So I want you to just look around for a second. The room you're sitting in, the screen you're looking at, maybe the sky outside your window. It's all illuminated, right? But have you ever stopped to ask yourself the ultimate physics paradox? Is the light we see every single day made of tiny physical particles? Or is it this continuous flowing wave? It's literally a question that has kept the absolute greatest minds in human history awake at night.
Welcome to This Explainer. Today, we're going to bridge the gap between two totally opposing worlds of physics and demystify the ultimate building block of the universe's most vital resource. We are talking about the photon. So, let's dive right in. Okay, here is our roadmap for today. 1. The mystery of light. 2. Meet the photon. 3. The color spectrum. 4. 6 properties of photons. And finally, 5. Energy and motion. Let's jump straight into Section 1, the mystery of light, Newton versus Hooke. Because, before we could even understand what light actually is, scientists had to basically argue over how it behaved.
And man, you had a clash between two absolute scientific giants here. On one side, you've got Isaac Newton. Now, Newton was firmly in the particle camp. He believed light was made of physical matter, almost like tiny little bullets shooting out of a light source. But then, on the flip side, you had Robert Hooke. He was this brilliant thinker who argued passionately that light was a wave, acting way more like a ripple flowing through water. And this historical debate, Newton's particles versus Hooke's waves, it raged on because, well, depending on the exact experiment you ran, light seemed to act like both. It was an absolute scientific stalemate.
So, how do you solve an impossible paradox where both sides somehow seem to be right? Well, you combine them. Moving to Section 2, meet the photon, the building block.
Okay, so by definition, a photon is the smallest discrete amount or quantum of electromagnetic radiation. Basically, it's the absolute, foundational, indivisible building block of all light. You cannot have half a photon. It is the basic unit. Think of it this way. If light were a staircase, a photon is a single step. And we actually owe this thrilling scientific resolution to a very familiar face, Albert Einstein. He was the one who developed this revolutionary quantum concept, essentially proving that light comes in these little discrete packets of energy. But, here's a fun fact, he didn't actually give it its famous name. Yeah, it was physical chemist Gilbert N. Lewis who coined the incredibly catchy term photon a few years later.
All right, now that we know what a photon actually is, let's shift gears a bit, from abstract physics over to human biology. Section 3, the color spectrum, seeing light.
So photons make up this massive, mostly invisible scale that we call the electromagnetic spectrum. All the way on the far right, you've got these huge, stretched-out radio waves and microwaves, and then on the far left, you have tiny, tightly packed, super-energetic gamma rays and X-rays. But what's really wild to think about is that the vast majority of this entire spectrum, it's completely invisible to us.
But if we zoom in super tightly on that one tiny, narrow slice right in the middle, we find the visible light spectrum. This is literally the only part of the whole electromagnetic spectrum that our human eyes can actually see. We perceive the different wavelengths of these specific photons as colors. Think back to good old Roy G. Biv in grade school, red, orange, yellow, green, blue, indigo, and violet. Our eyes are specifically, and highly biologically, sensitive to just 3 primary wavelengths, red, green, and blue. So every single color you have ever seen is just your brain decoding photons vibrating at these specific frequencies. It's wild.
But this actually brings up a really fascinating contrast. What about black and white? Well, technically speaking, black and white are not actually colors at all in the traditional sense. Black is simply the absence of all colors, meaning literally no visible photons are reaching your eyes. White, on the other hand, is the exact opposite. It's the presence of all colors hitting your eyes all at once.
Let's ground this in reality for a second. Think about your wardrobe. Why does a black t-shirt get so incredibly hot when you wear it on a sunny day? Well, because it's absorbing almost all the photons. It takes in all those different wavelengths of light and traps their energy as heat. A white t-shirt, conversely, reflects all of those wavelengths right back out. It's bouncing the entire visible spectrum away from your body, which keeps you cooler. It all comes down to how different materials interact with these photons.
Okay, let's pivot back to the meticulous, hard physics that dictate exactly what a photon can and cannot do. Section 4, 6 properties of photons. Here's a quick, high-level roadmap of the 6 absolute properties that govern a photon's existence. Number 1, duality. 2, constant velocity. 3, zero mass. 4, it carries energy and momentum.
5, it can be created and destroyed, and 6, it undergoes particle-like collisions with other matter, like electrons. Let's break down the most mind-bending stats from this list right now.
Let's start with duality. Remember that historical debate between Newton and Hooke? Well, turns out they were both right. A single photon acts as both a particle and an oscillating wave simultaneously. It travels as an electromagnetic wave through space, but then it hits and interacts with matter as a discrete particle-like packet of energy. So it's not one or the other, it's literally both at the exact same time. Mind-blowing, right?
Then there's property number 2, constant velocity. Photons are always moving, always, and in the empty vacuum of space, every single photon moves at the exact same staggering velocity, 2.9979 times 10 to the 8th power meters per second. That is the universal speed limit. It's what we casually refer to as the speed of light, and it's just an absolute constant for these little packets of energy.
But here's where it gets incredibly counterintuitive. Property number 3, zero mass. Wait, what? Zero? Yeah. Despite carrying energy, despite having momentum, and despite being totally capable of colliding with physical electrons, a photon has absolutely zero mass and zero rest energy. Like, if you could somehow stop a photon, which you can't, but just say you could, it would literally weigh nothing. It only exists in motion.
And that ties perfectly into property number 5. Because they have no mass, photons essentially pop into and out of existence. They are destroyed and created entirely through the absorption and emission of radiation. So when an atom gets excited, it emits a photon, creating it instantly. But when that same photon hits your black t-shirt, it gets absorbed and is instantly destroyed, just transferring its energy into heat.
This whole constant creation and destruction thing brings us perfectly to our final part today. Section 5, Energy in Motion, a photon's journey.
I want to pose a direct, everyday sort of question to you. If light travels continuously at millions of miles an hour, does it ever just run out of gas? Like, does it actually lose energy as it travels?
Think about a really relatable example. You turn on a flashlight in a dark setting, maybe exploring a creepy old house. The beam starts out intensely bright right there at the bulb, but as you look further out, the light just fades into the darkness. It really seems like the light is losing power, right?
Well, the scientific answer is a little more nuanced. Individual photons don't slow down, but the collective beam does lose energy. Light scatters and loses energy the further away it gets from its source. It's not that the individual photons just get tired and stop moving. It's that they're constantly colliding with dust particles, air molecules, you name it. Every time they hit something, they get absorbed, destroyed, or scattered. So the energy spreads out thinner and thinner across longer distances until, eventually, the visible light just fades away completely.
But that leaves us with one final, totally mind-bending cosmic question. If a single photon is emitted by a star, and it shoots out into the completely empty vacuum of space, where there is literally no dust or matter to hit, does it carry its energy at the speed of light through the universe forever? Could a photon born at the absolute dawn of time still be racing through the dark void right now, just waiting for a destination? It is an incredible thought, and it really makes you appreciate the deep, mysterious nature of space, energy, and the beautiful duality of light. I really hope this explainer illuminated the brilliant world of the photon for you today. Keep asking those big questions, keep looking up, and I'll see you next time.